All right, welcome back. Today, we are diving deep into what might just be the single most critical piece of the entire pyrolysis puzzle. Chapter 5, we're talking about critical contaminants. It's the one question that really hangs over this whole industry. I mean, we've got this incredible technology, right? We can take mountains of plastic trash and turn it back into a valuable oil. So why isn't it powering our world? Why aren't refineries just lining up to buy this stuff? What's the holdup? Well, the answer, as it turns out, is something of a closely guarded secret in the refining world. It's what we're calling a hidden poison list. We're talking about contaminants so dangerous they can literally destroy multi-million-dollar equipment, sometimes in just a matter of hours. And today, we're going to expose that list.
So here's how we're going to break this down. First, we'll look at the miracle oil's big problem. Then, we'll uncover that poison list and get to know the main suspects. After that, we're going inside the refinery crime scene, meeting the accomplices, exposing a really deceptive disguise, and then we'll get to the final verdict.
Okay, so let's set the scene. You've got this pyrolysis oil, and it looks so promising. But the biggest customers out there, these massive oil refineries, they're often giving it a hard no. And look, they're not just being difficult. They're trying to protect themselves from something nasty hidden deep inside that oil. For them, this isn't just some small inconvenience. It's a legitimate, existential threat to their operations.
All right, let's get right into the investigation. It is time to unseal the file on this poison list and really start profiling the main suspects, the ones holding this whole industry back.
So the technical name for these culprits is heteroatoms. Now, a pure fuel, that's basically just hydrocarbons, right? Just long chains of carbon and hydrogen atoms. Heteroatoms are, well, they're any other element that crashes the party. And you got to think of them as these awful unwanted guests who aren't just rude, they're literally there to burn the whole house down.
Okay, our first and most wanted suspect, chlorine. We're calling it the wrecker, and for a very good reason. Let me be clear, in the entire world of oil refining, there is probably no single contaminant more feared than this one.
So where is this stuff coming from? Well, the number one source is PVC, polyvinyl chloride. That plastic is about 57% chlorine by weight. But it's sneaky. It also hides in things like food wrap, flame retardants, and even those tiny little PVC labels on PET bottles that are so easy to miss when you're sorting waste. And get this, just a tiny amount can poison an entire batch of oil.
All right, next up on our poison list is oxygen, who we're calling the energy thief. Now, unlike chlorine, oxygen isn't this violent thug that destroys equipment. Now, its game is much more subtle. It quietly steals the value, the potential, right out from under you.
And what's really interesting here is where this oxygen comes from. Sure, it's in PET plastic, your soda bottles, but it's also a main component of biomass, like wood and straw, and even paper and cardboard. These are materials we usually think of as good, right? But in pyrolysis oil, they introduce oxygen that just acts like dead weight. It lowers the fuel's energy content and makes the whole thing unstable.
Suspect number 3 is nitrogen. This one's a silent killer we're calling the catalyst assassin, and its main job? To take out a refinery's most important and most expensive tools.
So, nitrogen finds its way in through stuff like nylon from old clothes, polyurethane foam from cushions and insulation, and even from the proteins in any stray biomass that gets mixed in. Once it's inside the refinery, it goes right after the catalysts. These are the chemical workhorses that make modern fuels possible, and nitrogen just poisons them, making them totally useless.
And that brings us to our final main suspect, sulfur, or the public menace. This one's notorious not just for the havoc it wreaks inside a refinery, but also for the serious environmental damage it causes. When you actually burn the fuel, creating things like acid rain.
Now, here's the key takeaway, the really crucial point. While sulfur can come from a few places, the overwhelming source in the world of pyrolysis is end-of-life tires. See, that vulcanization process that makes tires so tough? It uses a ton of sulfur, and pretty much all of it transfers directly into the pyrolysis oil. That one single fact pretty much defines the entire challenge of recycling tires this way.
Okay, so we've identified our main suspects. Now, let's step inside the refinery and examine the crime scene. What kind of damage are these big four actually doing?
The wrecker, chlorine, is brutal. It has this devastating two-pronged attack. First, when things get hot, it forms hydrochloric acid gas that literally eats right through stainless steel. We're talking pipes bursting. But that's not all.
If nitrogen is also hanging around, they team up to form solid ammonium chloride salts that just clog up vital pipelines, forcing a sudden, incredibly expensive shutdown.
And this is where you can really see the scale of the problem. Check this out. A super sensitive, high-value piece of equipment, like a steam cracker, can handle maybe 5 parts per million of chlorine. 5. But raw pyrolysis oil? It can have over 1,000 parts per million. I mean, it's not even in the same sport, let alone the same ballpark.
And what about our public menace, sulfur? A typical batch of raw oil from tires can have something like 15,000 parts per million of sulfur. The legal limit for the diesel you put in your car? 10. Just 10 ppm. That is a mind-boggling difference. And getting all that sulfur out is a monumental challenge.
But, the Big Four don't work alone. No, they've got a whole crew of accomplices. We're talking metals and solids that help them carry out their destructive plans.
So you've got alkali metals like sodium and potassium. They just wreck catalysts. Then you have heavy metals like zinc, mostly from tires, which deactivate them. Silicon is another bad one. It forms this glassy, unbreakable shield right on the catalyst surface. And finally, you've got these tiny abrasive char particles that are like sandpaper, just grinding down pumps and injectors from the inside out.
Okay, but now we get to the big twist, the one detail that makes this whole mystery so incredibly hard to solve. And it brings us right back to our public enemy number 1, chlorine. Because it turns out it wears a very, very deceptive disguise.
You see, not all chlorine is created equal. First, you have inorganic chloride. Think of it like simple salt. It dissolves in water, and refineries have a standard piece of gear called a desalter that can just wash it right out. Easy enough. But then there's organic chloride. And this is a whole different beast. Here, the chlorine atom is chemically bonded to the oil molecules themselves. It's oil-soluble. It stays hidden, and it is extremely dangerous.
So here's how the attack plays out. The organic chlorine, in its disguise, enters the refinery. It's completely invisible to that water wash, so it just sails right past the primary defenses. Then it travels deep into the hottest parts of the plant, and only then, when it's too late, does it break down and release that corrosive hydrochloric acid gas right where the refinery is most vulnerable. The result? Catastrophic failure, often with absolutely no warning.
So, after looking at all this evidence, the final verdict is in, and it's crystal clear. The case against using raw, untreated pyrolysis oil is just overwhelming. Purification isn't just a nice-to-have or a good idea, it is absolutely 100% mandatory.
This traffic light system really sums it all up perfectly. For the really bad stuff, like chlorine and those alkali metals, the acceptable green level is down in the single-digit parts per million. We're talking less than 10. Anything over, say, 50 ppm of chlorine is an absolute red. A critical failure. That's a level that would get the fuel flat out rejected. This is the standard that has to be met, period. So, that's where we'll close our investigation for today. We've identified the poisons, we've seen the crime scene, we understand the damage they cause, and all of this leaves us with one final crucial question. Now that we know exactly what the problem is, what is it actually going to take to clean up this incredibly promising fuel and finally unlock its true potential?